let's actually, Amy, build a spaceship and do some space traveling. Let's suppose we have the ability to build spaceships that people can live on for several years. Proxima Centauri is the closest star to the Earth. If we did build a spaceship, it's probably one of the first places we would send someone because it's the closest star. We'd like to see what else is there. It's 4.24 light years away. What's a light year? A lot of people, because they see the word year, think a light year is a measure of time. A light year is a measure of distance. It's how far light travels in 1 year. So it takes light 4.24 years to reach us from Proxima Centauri. Suppose we build a spaceship that can travel at 80% of the speed of light. How long will the spaceship take to get there as measured by stationary observers on the Earth? Grace, what's this question asking me to find? Time. Now here's the question. Time or time zero? Is it asking us to find time on board the spaceship? No. Here's what it wants us to find. Measured by, can you read me that phrase right there? All of you underline that. Did they tell me time on board the spaceship anywhere? No. They did. Okay, 4.24 is not a time, it's a distance. 4.24 light years is a distance. This is not a relativity question yet because the Earth is at rest. So I agree with you, Grace. It wants me to find time back on Earth. But I'm going to find time. Well, first of all, Grace, what's the velocity that the spaceship is going to be traveling away from the Earth at? So v is going to be 0.8 c. I'm not using t and t0 and the square root of blah, 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 because we haven't yet brought relativity in because we're staying at rest on Earth. Instead, I'm going to use a distance, and the distance is 4.24. And my abbreviation for light years, there probably is a proper abbreviation, and I keep forgetting to look it up. I use a lowercase l, and I think I've already told you I always make my lowercase l's cursive. Otherwise, if I made it printed, it would look like 4.21, and I don't want to remember that later. And then I'm going to use the letter Y for years. Aren't you supposed to use letter A for years? Yeah, just light years. I'm going to use that. Acceleration is still 0. What I'm actually going to do is I'm going to use this basic equation. Speed equals distance times time. Why am I not using the relativity stuff yet? Because we're on the Earth. We're not moving at relativistic speeds yet. Grace, how would I get the t by itself? Divide by v is correct. So time is d over v. It's going to be 4.24 light years all over 0.8 c. Look up, everybody, for 1 second. Grace, what does the L period Y stand for? What does the L stand for? Say it again. And the C stands for the speed of? Same thing. Speed of light. So what does the L stand for? Light. Speed of light. What does the Z stand for? Speed of light. Even though they're not the same letter, I'm going to argue that those do cancel, and we get an answer in years, which is time. This is how long we on Earth think it will take a spaceship traveling at 80% of the speed of light to get there, relative to the Earth. What's the answer? Now you want to get out your calculator. What'd you get, folks? I think this works out nice. Not evenly, but like to 2 decimals or something like that. Sorry? 5.3 years. So as far as we're concerned, if they left, let's say, January 1st, 2020, they would get there 2025, and then 0.3 of a year is about a third of a year. January, probably sometime in March or April. As far as we're concerned. Yeah. Oh, that's a stretch. Okay. Now, B. Grace, what's B asking me to find? Time. Now we're going to kick relativity in, because now we're asking how much time for an object that's moving relative to us. See the difference? Good. T0. On your green sheet, look at the time dilation equation. Make sure you know where it is. And then ask if you can rewrite that to get the T0 by itself. Well, what's that square root doing to the T0, Grace? Adding, subtracting, multiplying, or dividing. So how will I move that square root over? What's the opposite of dividing? Multiplying. Is that okay? I'm hoping you can rederive that equation from there. So we're going to argue that T0 is the time back on Earth times the square root of 1 minus V over C all squared. Grace, what's the time back on Earth? That's why I had to do part A first. The time back on Earth is 5.3. Square root 1 minus 0.8 C over C all squared. Grace, do you see? Do you see? Do you see? What do you see? Now, apparently I have to explain this because in my last block, someone didn't get the terrible pun that I'm making. When I'm saying, do you see? Do you see? Do you see? What do you see? I'm really hoping that you're looking at the letter C in the top and the bottom of the fraction. We got that okay? Because one person didn't get that last class. I don't get it. So, okay. Type that in. Mr. Dueck, could I type that in one step? Yeah, if you wanted to do this in one step, it would look like this. 5.3 times square root bracket 1 minus 0.8 all squared. So we think it's going to take 5.3 years, and it will for us, but how much time will elapse on the spaceship? 3.18? And that's years. Just for nerdishness, Mila, if they were running a mission, so let's say that they traveled there, which took them 5.3 years relative to us, and then they stayed there for a year, and then they came back, we would say this was an 11.6 year mission, but the astronauts would travel on the ship for 3.18 years. Once they got there, they would be at rest relative to us, so time would move normally for that 1 year that they were exploring, the same as us, and then they would come back for 3.18 years. The astronauts would have aged 7.36 years. And we talked about that yesterday, and although that's weird, that's not the really weird part. It gets better, but weirder, but cooler. Let's suppose the astronauts decided that they were going to string out a cosmic tape measure behind them, and they were going to measure how far they traveled. They were going to measure how far it is from Earth to Proxima Centauri. Mr. Dueck, isn't it 4.24 light years from Earth to Proxima Centauri? It's relative. It's all relative. You see, here's what the astronauts would do. They would do the same step as we did in part A, because as far as they're concerned, inside their spaceship, they're at rest relative to their spaceship. So they would say, oh, the distance that we're traveling is speed times time. How fast is their speed? Well, how fast is the spaceship traveling? 0.8 C. This is on board the spaceship, so instead of a T, what I really should have put in the equation is a T0. So if all of you look up, no, I added this after. I said, really, it should be speed times time on board the spaceship. Kyle, how much time elapsed on board the spaceship? Not 5.3 years. What? $3.18 what? Say it again, Kyle. I want you to notice in the units, what does the letter C stand for? The speed of? We actually get light years back in our units, which is a measure of distance, so this is going to work. What is 0.8 times 3.18? How many light years? What'd you get? Oh, I thought someone said an answer. Grace, you started us. Finish it off. Take it home. What do we get? 2 point what? Is it 2.544, something like that? I'll go to 2.54. What does that mean? It means not only is time not the same anywhere in the universe for objects that are moving, the distance that they travel is different. It is impossible for us to say with certainty how far away from Earth anything is. It all depends. Are you moving relative to the Earth? You'll actually, Sahara, measure a different distance. You'll actually travel through a different distance than we who are measuring from the Earth would measure. How does that work? Well, remember that speed, don't write this down, is distance over time. And you always have to get the same answer if you're measuring the speed of light. If you're moving, not only is time going to be different, but space is going to be different as well. The universe will conspire to make sure that you always get the same result when you try and measure the speed of light. How? It'll muck around with time, but it will actually warp space in front of you. It will compress space in front of you to make sure that that explains why you didn't have to travel as far a distance, and that's why time was moving slower for you. Distances are relative as well. How far away is something? Generally in astronomy, we're always giving that answer relative to the Earth at rest. But again, if you actually flew the spaceship there, you would find you didn't travel that distance. You traveled a shorter distance. That's weird, but kind of cool. Turn the page. Or next page over. Let's use our Einstein imagination and let's pretend that we're in a spaceship that is traveling at the speed of light. How much time would elapse on board the spaceship? Matt, what's this question asking me to find? On board the spaceship, because the Earth is not traveling at the speed of light. So this is wanting us to find time on board. Did they tell us how much time has elapsed back home? How much in example 5? In example 5. Did they tell us how much time has elapsed back home? No. You know what? Let's pretend 1 second. Let's look at, for every second back home on Earth, if you were traveling at the speed of light, how fast would you be traveling? Oh, and I guess that means that V equals C, the speed of light. Matt, can you get the T0 by itself in the time dilation equation, please? Times the square root thingy, yes? Times the square root thingy. Yeah, I got you. Eventually, you're going to learn, we call that the gamma function. And so we would say T times the gamma. That I'll teach you to abbreviate, but that's next lesson. So if I put in a 1, square root of 1 minus, this time we're traveling at the speed of light over C all squared. Matt, this is so weird and so easy that even you don't need a calculator. Are you ready, Matt? What's 5 divided by 5 in your head? What's 10 divided by 10 in your head? What's C divided by C in your head? What's 1 squared? What's 1 times 1? What's 1 minus 1? What's the square root of 0? What's 1 times 0? If you're in a spaceship moving at the speed of light, how much time elapses for you? None. Nothing. If you're moving at the speed of light, time does not exist. Look up. I'm going to use my smartphone, and I'm going to create some photons. Behold, ready? 1, 2, 3. And you just saw some photons wink into existence because you see some light. That's what you saw, Isabella, relative to you. The photons, which are traveling at the speed of light, don't experience time at all. So even though you saw them wink into existence 10 seconds ago, as far as the photons are concerned, they have seen all times in the universe at once. They saw the Big Bang, and they're also simultaneously seeing the end of the universe right now, because they don't experience time at all. Told you light is special. We like to look out at night and look at the stars, and you may have imagined to yourself, Ange, oh, that star is so far away. That light took 100 years to reach the Earth, or 1,000 years to reach the Earth, or 10,000 years to reach the Earth. That's only relative to us. As far as those photons are concerned, if they could think, they left the star, they arrived at the Earth, and there was no time in between on their journey because they don't experience time at all. So, for our stationary frame of reference on Earth, we like to say that it can take light from stars thousands or millions of years to reach us. In actual fact, relative to the beam of light, how much time has passed? Nothing. That's the universe we live in. Light is special. Light is really neat. Example 6. Example 6. Amy, what's example 6 asking me to find? Time on board the spaceship. Why is this question a little bit weird? Can you see it? What's a bit different here? I gave you the speed in meters per second, not as a percentage of light. Don't panic. Here we go. What did you say they're asking us to find, Amy? Time on board. So that must mean they gave us time back on Earth. How much time elapsed back on Earth? 100 years? What's our speed? Read it to me. Meters per second. What that means is, do you see is not going to work. I'm actually going to have to put a number in for C. That's on your green sheet on the back page. Make sure you know where it is. You might end up memorizing it because it's a fairly easy one to remember. What is the speed of light in meters per second, Amy, exactly in meters per second? Yep. And you're going to have to make sure now that you know where your scientific notation button is on your calculator, because this one's a bit weird. Let's be a bit more careful. So again, we're going to get the T0 by itself, which means it's going to be T times the square root of 1 minus V over C, all squared. What did you say that T was? 100. Big square root of 1 minus, and then I guess on the top, I'm going to have 2.85 times 10 to the 8th. And on the bottom, now I actually have to plug in the number 3 times 10 to the 8th, all squared. I would probably start with the bracket. So if you want to follow along, you can. And some of you may be able to do this quicker depending on your calculator. But I would probably start with 2.85 scientific notation button 8 divided by 3 scientific notation button 8. And when I do that, I get 0.95. Is that okay? Squared. I get that. 1 minus that. I get 0.0975. Square root. And then times 100. And you should get 31.2 years. You get that okay? Nodding? If not, you'll have to practice that in the homework. So, 100 years back, home on Earth, 31.2 years on the spaceship. So there will be, Amy, at least one question in your future quiz test where I give you the speed in meters per second instead of a percentage of the speed of light, and you can't do the do you see, do you see, do you see, what do you see? Good job. Cool. Example 7. Armand, what's example 7 asking me to find? You know what? I think it's asking me to find V. I used to be mean. I used to actually make my students get the V by itself from this equation here, and it's doable. I've mellowed. On your green sheet at the bottom, do you have several equations for V? Yeah. Find the one that applies to what we're doing here. You'll notice some of them have M's in them, some of them have L's in them, but I think there is one that has times in them. By the way, we'll be doing the other ones next lesson, which I haven't got there yet. Which is the speed equation with time? Can you read it to me, kiddo?
Yeah. E equals C squared root 1 minus E0 over 2 divided by.
I'm going to write that as T0 over T all squared because that's easier on my calculator. You okay with that little tweak? Okay. Temporarily, Armand, I'm going to leave the C as a C. I can make it 3 times 10 to the 8th later. I'm just going to do the square root thingy first. So I'm going to have 1 minus, what was T0, time on board the spaceship? You'll notice this time, Ethan, I didn't make a list. I'm seeing how good we're getting, and I'm going to see if we can take a little shortcut. If not, I would make my list. What's time on board the spaceship? Yep. What's time back home on Earth? By the way, don't forget the squared. What I'm really doing, Armand, is I'm saying how fast would I need to travel if I wanted the spaceship to age half as fast as Earth? Because I set up a 2-to-1 relationship. I could have done 1 year, 2 years, 10 years, 20 years, 100 years, 200 years, but time on the spaceship is going to move half as fast. Okay, just do the square root thingy. (10 divided by 20 equals squared 1 minus that square root of that. You get 0.86602, 0.866? Get that okay, Mila? Yeah? Armand, you get that okay? You're still typing, sorry. Okay, so you went 10 divided by 20. Type 10 divided by 20. Hit equals. And then do the squared. Hit equals. Then do the 1 minus that. Hit equals. And then what's the last thing we have to do? Square root. And hit equals. And you should have 0.86602, that. Yes? So what I have is C times 0.86. You know what? I'm going to write it like this, 0.866C, because that's usually where we put the letter. Psst. Look at what we just wrote. What percentage of the speed of light is that? Kai, can you read to me exactly as I wrote there without rounding off at all? What percentage of the speed of light is that? It's 86.6% of the speed of light. If I don't put the C in as a number, if I just let it tail on, I'll actually get an answer as a percentage of light. If you're wondering how I was making up the questions that we did earlier, this is how I was reverse engineering them. Okay, so we can say this. V equals 86.6% of C. What if I wanted that in meters per second instead of as a percentage? What does the word of mean in math? Yeah? Multiply. And then what's C as a number exactly? Times 10 to the... I already have this sitting on my calculator. I'm going to use my answer button. Times 3 scientific notation button 8. If I ask for an answer in meters per second, the answer in meters per second is 259807621. You know what? I'm going to round off on the 0, and I'm going to write this in scientific notation. 1, 2, 3, 4, 5, 6, 7, 8. 2.598 or 2.598 times 10 to the 8th meters per second. Mr. Dueck, which answer do you want? In the homework, do your answer both as a percentage and in meters per second. On the test, I will say to you either, give me the speed as a percentage of the speed of light, or I will say to you, give me the answer in meters per second. We can now find a speed. Turn the page. By how much is time expanded, or how much does the clock slow down? Fancy word, what's the dilation factor? From a fixed observer's point of view, Earth, if a spaceship is moving at 1/2 the speed of light. Huh? This question is asking this. What happens to time on board the spaceship compared to the Earth? Matt, did example 8 tell me time back home on the Earth in the question? I thought you'd get it the second time. I came back to you and I thought, oh, he'll get it this time. Let's try this again. Matt, did this tell me time back home on the Earth in this question? No. So you know what? Let's let time on the Earth be 1 year, hour, second. I don't care. 1. V is 0.5 C. And let's see what T0 gives us when we let T be 1 and V is 0.5 C. We're going to get T0 equals, let's see if we can plug numbers straight in. 1 square root of 1 minus 0.5 C over C all squared. Do you see? Do you see? Do you see? What do you see? Do you see? Do you see? Do you see? What do you see? Do you see? Do you see? Do you see? What? A little participation from the audience here, folks. By the way, Ange, will multiplying by 1 in front of everything make a difference at all? So we actually call this 1 minus V over C all squared. This is the time dilation factor. And so if we crunch that, Diego, what do you get? You get 0.866. So what does this mean? This means that for every second back home on Earth, 0.866 seconds ticks by on the spaceship. Or you can say it moves 0.866 or 86.6% as fast as the Earth. Or if you want to, you could go like this, 1 minus 0.866. You could say, oh, time is moving 13.4% slower on the spaceship than it is back home on Earth. Usually we just say this is the time dilation factor. Every hour on Earth is 0.866 of an hour on the spaceship. Every day on Earth is 0.866 of a day on the spaceship. And that adds up over time. That's at half the speed of light. What if we go at 80% of the speed of light? We're going to walk through the same argument, Matt. We're going to say, okay, I want to find time on board the spaceship when time back home on Earth is 1 second, 1 minute, 1 year, 1 week, one whatever. It's going to be the square root of 1 minus 0.8 C over C all squared. Your hint for this one is I think it actually works out evenly. You don't get a long, non-repeating, yucky decimal. And of course, all of you are trying these on your calculator because this is fairly hefty plug and chug. It's plug and chug, but it's pretty complicated plug and chug. Alec, what'd you get? So when I said, and of course all of you, and you saw me staring at you, did you think my next step wasn't going to be to call on you? Come on, get with the program. Caleb, what'd you get? 0.6 even, yeah? So if you're going at 80% of the speed of light, for you, time is moving 60% as fast as somebody who's at rest relative to you. Yeah. That's a great question. I really didn't put any units in for the time. I'm just calculating the factor. So I would say 0.8866 as fast as Earth. It's technically not units for that one. No. Thanks for asking. I was curious when I didn't put any units if someone, because I've trained you, units. I did the Verizon phone call for you at the beginning of the year to teach you that units matter. It's a factor. So I would need to know what actual units are you measuring time back on Earth in, and now I can tell you what the answer is in those units. Okay. Important note. For now, we are assuming that A equals 0. Einstein, at this point, did not know how to work acceleration into his equations. In fact, the theory of special relativity should actually be called the theory of special case relativity. And what's the special case? A is 0. Einstein published the theory of relativity in 1905. Took him 10 more years to figure out the math to work in acceleration. And then he realized gravity is a form of acceleration. I've just come up with a much better explanation for how gravity works. It's a warping of space and time, kind of like we've been talking about so far. What's your homework? So your homework is every question. You can do these on a separate piece of paper. I've put the answers online. There's a full answer key on pitmath.com underneath your block. And I did attach the answers at the end. So all these ones that I didn't circle, they are now homework as well. So we can circle 15, 16, 17, 18, 19, 20, 21.